So hello everyone, thanks to be here today. So first, I'm Alexo Rotondi. I'm a PhD student in the MIT team. And today we have two presentations, one of Amael Montmoreau and Kunho. And we are going to start with Amael with the estimation of respiratory motion from the ECG and its impact on arrhythmia mapping.
Thank you. Hello, everyone. So my name is Amael Montmoreau. I'm working as a postdoc to the Traitement du Signal team, more specifically on two project with Laura Beer as an advisor and Ayoub Ejibuli, sorry. So today, I heard that we are just two speakers, so we will have plenty of time to present our project. I had two choices. So one of them was to make your ears bleeding a longer time because of my English or my French accent, or the second one is to let you enjoy a longer time the French, the Friday drinks. Of course, the choice has been made really quickly. Your ear will bleed a longer time, just a bit, don't worry. So today I will present one of my projects, which is the estimation of respiratory motion from the ECG and its impact on arrhythmia mapping. First, I want to give you a basic overview of what I'm doing here. So here is my rather professional slide. So why I'm here? I'm here to help practitioners to understand if you want, understand why some people can have sudden death and where is the source of this problem on your heart. And I want to do that without putting anything in your body. So how it's possible? So imagine that you could put your bleeding hair on your torso and you can talk to your heart. Okay, let's have a talk. How are you, dude? Here's my heart hanging from the outer. Oh, I'm really fine. You are really stressed right now, but yeah, I'm okay. Oh, no. Oh, maybe I would let you down in a few years or a few months, I don't know. Okay, I didn't expect this answer. What can I do to avoid that? Well, it's pretty simple. Just burn me here, dummy. Okay, I think that all the practitioners would like to hear that. Burn me here. Here's the localization of my problem. Well, could be cool, right? We are not so far from that. If you replace your ear by 128 electrodes and the voice of your heart by electrical signal, here we are. I can listen your heart. But there is a thing. Between your heart and your torso, you have a lot of stuff. Muscle, lung, fat, extra. So I will not have all of it. I will lose some word. For example, I will hear, burn me, dummy. Well, it's useless. I can't burn everything. So I need to catch this simple but really important word here, the localization of my problem. So to do that, just replace I'm sorry. So, okay, here is my project. So to prevent that, I will use the electrocardiogram imaging, so it's CGI. I will give you a basic definition of what is the CGI and how I will implement this technique. So first, the CGI has been emerging as a way to diagnose a cardiac dysfunction. And the idea of the CGI is to combine the body surface potential that we can record with these 128 electrodes with the 3D anatomic imaging of your heart and your torso. And with that, I want to be able to reconstruct the heart's electrical activity and find where is the problem. And to do that, I need to solve the CGI, the inverse problem, to find the CGI. Because you have to know for the CGI, you have two kinds of problem, the forward and inverse problem. For the forward problem, you know the source Hertz electrical activity and you want to find the body potential surface. So it's relatively simple because you have one solution. But you are running into problems when you want to do the inverse problem, because from the body potential surface that you know, you have multitude of possibility about the source Earth's electrical potential. So to be able to solve this problem, you need to define a cardiac model, the torso model, to use some mathematical trick like regularization. I use, for example, Tikhonov, etc. So you will lose some information, but you will be able to reconstruct the Earth's electrical activity. Well, you have to know also there is other approach, actually, the machine learning. We are working on it right now, but it will be for another presentation. So, okay, now we know how it works. Now we want to know if this technique is accurate or not. So I will show you some model validation has been made. So for example, this one is really amazing. So it's an ex vivo experiment where they use a socket. There is a multitude of electrodes on this socket. You put they put the beating heart inside, and they put the beating heart with the socket inside the empty torso tank, which has also a multitude of electrodes. And they add a conductor liquid to reproduce the conductivity of the human body. So with that, you have the Hertz electrical activity and the body surface potential. So now if we compare the two Hertz electrical activity and the reconstruct Hertz electrical activity, you can see that the electrogram cross correlation here is pretty good, so more than 0.8, and the localization error is between 2 and 10 millimeter. So it's pretty good. But when you're looking for in vivo models, so experiment, for example, human, dog, and pig, you will see that the results are really different. So the electrogram cross correlation is lower, around 0.7, and the localization error is around 10 with big uncertainty here. So why there is such difference between these two kind of experiment? So it could be the homogeneous assumption, maybe the cardiac models they used for each experiment, or the respiratory motion. And it's on this last one I will work. So why the respiratory motion? When you have to imagine, when you are breathing, you have your heart here, and your torso with the electrodes here. So when you are breathing, the torso and your heart will move. So the distance between electrodes and your heart will change, the resistivity will change. So the signal that you are recording will change. You can see here, very easily here. So I took signal from one of the electrodes. You have here 1 bit, 2 bit, etc. You see here, so this peak is a R wave peak. And you see that the amplitude of the R peak will move over time. And if you compare with the respiratory motion we measured with this belt, you can see that there is a high correlation between the respiratory motion and this variation of this R amplitude. So we know that the respiratory motion will impact the ECG. Now we want to know if the ECG could be impacted by the respiratory motion. So the idea is to take, for example, 2 or 3 bits here to the maximum inhalation, and to proceed to apply the CGI reconstruction. Do the same with the 3 bit, for example, for the exhalation experiment, and to compare both of them and see if there is a difference in the CGI reconstruction. But there is a problem here because the data I'm using has not this recording respiratory motion. So I need to estimate this respiratory emission. It exists several techniques, methods, so I have to choose the best of them. I remember you that I'm using 128 electrodes. For some of these methods, I will select just one electrode. And with this signal, I will be able to find some feature like the R peak amplitude, like I told you before, the R peak interval. So it's the time between two R peak. And the QRS interval, sorry, so it's the integral of the QRS. I also made the PCA, so principal component analysis, from the 128 electrodes. And I choose, I select the first component of this PCA. I measured this R peak amplitude of this PCA. So now I have 4 methods from the ECG. I tried also to find other methods from the vector cardiogram. I don't know if you know what is the vector cardiogram, so I will give you a basic definition. You have to imagine you have several electrodes, and you will project the signal of this electrode in the 3D space. And this 3D space will be your vector cardiogram. So we select the QRS inside this signal, and when you project this QRS, you will see this loop in this vector cardiogram. So one loop, one bit for each loop. And from this vector cardiogram, I will be able to find a lot of features who could give me the estimated respiratory emission. So I select the 2 best of them. First of all, the angle between the loop max vector. So it's the max vector of one loop. I will compare it with the second loop vector, max vector, and I will calculate the angle between them. And this angle will give us the estimated respiratory emission. The second one is more complicated to explain. So it's I will choose the best component of my eigenvectors. I calculate from the angular value decomposition of one loop. And this component will give us the estimated respiratory emission. So now I have the methods, how I will compare them. So I choose 2 metrics, the correlation coefficient. You see the true respiratory emission in red, which I will compare with the estimated respiratory emission in blue. I select also the specificity of the bit classification, because like I told you, I need to select the bits inside the extremum of the respiratory emission. So I want to be sure that I will select the good bit in this area. So now about the result. So the VCG eigenvector is so far the best of them, because we have a good result for the cross correlation and the specificity, and also it's really robust. You can see we have always a good result during the time. The others are sometimes really, really bad. For example, for R peak, we can have a really good result, and for some reason, I don't know, for some other patient, you will have a bad result. So I will select this method, sorry, to estimate the respiratory emission. So now I need to see if there is an impact of the respiratory emission on the ECGI reconstruction. So I show you experiment with the peak data we used. It's a basic representation of what I'm doing here. You see here the estimated respiratory emission, and here's the bits I selected in this respiratory emission. Here you see a map of the standard deviation mapping of the ECG reconstruction between each bit here I selected. So here it's the bit in the inhalation area, here in exhalation area, and both of them for this one. You can see for the first one, the inhalation between each bit, you don't see a big difference. It's the same for exhalation, but when you add exhalation and inhalation, you see a difference here, around 5 milliseconds. So it's a lot when you know that all the activation time will take around 40 or 50 milliseconds. Sorry. So of course, it's the first result. I need to go further, use other data. I'm working on human data also to see if I can confirm this result. So to conclude, we could define a good method to estimate the respiratory motion. We could show that there is an impact of the respiratory motion on the ECGI reconstruction, but we have to confirm this result with more data. And then in the future, maybe if we confirm this impact, we will make sure that we are selecting, for example, the bit in the exhalation area to be sure there is no such difference and impact on the ECGI. Thank you for your attention.
Thanks for your good presentation. Any question?
Thank you for your presentation. Maybe I miss it, but on your result graph for the different method, can you explain why the error bar are so big?
Because for some patients, you have a really bad result. For example, I had like a cross correlation for RPIC, like 0.17. The reason about that is maybe because we are using just one lead. So if the signal is bad, or maybe the place of this lead is bad, I will have a bad result. But there is a thing I don't explain, is the PCA, because it's based on the 128 electrodes. So I should have always pretty good result. It was not the case neither.
Yeah. Sorry. So isn't it easier to just change the shape of the mesh you map it to the heart? Because we're talking about motion, and there is a figure that you show that the heart actually changed the orientation. So is there a plan to just maybe rotate the heart or change its shape for you to map it on?
Yeah, okay, but actually, okay, so but you have to know how the heart move for that.
Yeah, but for example, if you do breathe hold, so you do the scan without having to take a breath, and you know that let's just try to find a place where there is no breathing in the ECGI, and then you just map it to there.
Beautiful.
Oh, yeah.
Yeah.
No, I'm just asking if there any plan on like just changing the shape of the geometry of it.
The first step was to see how much. Sorry, the first step was just to see how much it did actually impact. So if the respiration ends up not impacting our results very much, then we don't have to do anything.
More question? No? So I think we continue, maybe? Yeah, thank you. Okay, so now we're going to continue with Kun and the advancing cardiology diagnostic capabilities, integrated application for AI-powered automated segmentation and myocardial scar detection and classification.
Thanks for your introduction, Alexi. Well, hello everyone. I'm the engineer in the imaging team and work on the project SM Hertz. And our team leader and also my supervisor is Aurélien Bustin. And now I will present the progress I've made on this project. So first, I will introduce the objective of our project. Well, when a patient has a cardiac condition, the doctor may ask him to undergo a MRI scan, and then the doctor will analyze the MRI results to provide a result, to provide a diagnosis. However, the current MRI systems are too slow, too complex, and mostly rely on manual analysis by experienced specialists. And that is time consuming. Well, in recent year, with the advancement of artificial intelligence, applying this technology in medical diagnosis could address, I think there's some problem. Could address the current challenges posed by slow, complex MRI systems. The aim of our project is to revolutionize the cardiac MRI systems by developing a fast one-click, fully automated imaging pipeline for cardiology. And my role in this project is to build a platform for doctors, enabling them to use a newly developed algorithm to diagnose a condition more effectively. So the platform is based on automated spot technique proposed by Aurélien Bustin. And well, we can see here in this figure, where is my, I don't know how to show that. Well, in this figure, we can use a spot method to extract both red blood and black blood images. And then with the introduction of the artificial intelligence, it becomes possible to extract left ventricular wall contours from red blood image, and which are then propagated to the black blood image. And then scar can be extracted. As shown in this figure, we obtain the fusion from black blood image and the red blood image, where the scar extracted from black blood image is overlaid onto the red blood image. And after that, the total and regional infarct mass, volume, and the scar transmutability can also be measured automatically. So this framework theoretically can save amount of time for diagnosis. And the conclusion of automated spot methods during the processing time of scar detection is approximately 10 seconds for automatic process, compared to 17 plus or minus 7 minutes for manual processing. So that is an interesting result for us. Based on this algorithm, we want to build a platform to make it easier for doctors to operate and better use this framework. So our platform is implemented based on an application, the existed application named MusicCardio, which is developed in C++ by the multimodal data science team at Lyric, and the Appian and Carmen INRIA teams, aiming to provide a wide range of functionality and processing pipelines for diagnosis and therapy guidance. And it is built on the open source software MedInReal, which includes a set of toolbox, for example, for image segmentation, filtering, mesh processing, etc. So and our platform currently is a toolbox in music audio software. So same as music audio, it is programmed in C++, and the application interface is implemented using the Qt library. And the image processing components of entire toolbox is implemented using the ETK library. So then I will demonstrate the functionalities that we've implemented in this application so far. I hope I can show it. No. So this is a music audio software. I suppose most of you maybe already use this application and quite familiar with it or not. So our platform is based on the segmentation section. And our platform is the first one named auto segmentation. Well, this toolbox is not yet available in the current version of music audio, but I hope we will add it in the near future, maybe. So the use of our toolbox involves diagnosing and analyzing after obtaining the black blood and red blood images. So first step is to load the black blood image. Okay, I just so to load the black blood and red blood images, and then we will display them side by side for better observation. And here we can see there are several functionalities. And currently, they're completely independent. That means we don't need to complete one before processing to another. But our goal in the future is to generate a pipeline where we can accomplish all functions in the sequence with just one click. So we have three main functionalities: the automated segmentation, and this one is for the scar detection, and this one is for the scar quantification. So first one, the automated segmentation. Here we can select the region we want to segment. For example, endocardium, epicardium, left ventricular wall. Or for example, epicardium. And here we have the AI models for segmentation. Here I loaded two AI models, both of which are trained on around 200 patients and over 10,000 images to get the segmentation automatically. And that's a work result of our colleagues, Victor 1.0 and Victor 2.0. So thanks for your works. For example, yes, and here we can change the color to display after segmentation. For example, we use this one, and to execute it. So as we can see here, the segmentation is displayed on all slices, so as to the black blood images. And then we can use this button to save the segmentation as a mask, which we can see here, and which we can use later. And if you are not want this segmentation anymore, you can just clear the mask and do another segmentation. For example, this time I choose a war region and the metformin model, and choose the red one that I used to use it. So let's do it again, just to show you that. So we can see we'll get the result of the wall segmentation on all the slices. And for the black blood image as well. So the next step is for scar detection. So we can get a scar view with click of this button that I already click it. And it take a little bit time. So then we can see the scar is displayed in this window on all slices. And in fact, we can adjust the intensity on black blood image to have a better view. Since I don't have the mouse, so it's difficult. So for example, here we can clearly see the scar, the white part in the wall region. We'll visually can compare it with the scar displayed here. For example, this one is slice 9. So in the black blood slice 9, where is it? So we can see, we can compare them. It's basically consistent. One thing I should point out here is that displaying the scar is achieved by using filtering the differences in pixel intensity of black blood image rather than use artificial intelligence to directly detect it. So that's one thing I should point out. And after that, we can use this button, get landmarks, to get the scar quantification. In fact, we provide two models, in fact, two bullseyes for scar quantification. And both of them are based on the automatically generated two landmarks, which can use to locate the region of bullseye or the start point of the calculation. The landmarks that I will show you later when the result comes out. It takes a little bit because I need to draw the bullseye that we will see later. If you have tiny question, you can ask now, and I can reply during the waiting time.
Could you just confirm, is the artificial intelligence model using both images to segment?
In fact, the segmentation is applied on the bright blood image, and we get the result, and I just put the result, the mask, on the black blood image, because the black blood image is used to detect the scar normally. And yeah, the scar detection. Exactly.
See if this works on animal experimental data that we have here based on learning from.
You mean the images?
AI models are based on learning from clinical segmentations. Have you guys tried it on any of the experimental MRIs from Exocean?
Oh, I don't get the, sorry, I don't get the question.
And so the AI models that you have, based on training on clinical data, correct?
Yes.
And you tested to see whether or not that training can be applied to the experimental MRIs for pick and shoot data.
For now, I don't know. I don't think so. No.
No, maybe later. Yeah, well,
Train a model with some kind of rotation difference because human have different benches to be the same rotation.
Yeah.
And your model is very rotation environment.
As I said, if you just train from the data, we have the.
Actually, we tried visual animals. How many patients did it take to train one?
around for the model UNet, around 200 patients. Yeah.
With the organization as well as with the data. Yeah, and the patient we have. It was always partial patients, so not only because it was training for the segmentation. Non-specific.
Okay, so next, when we you can see here we get the two landmarks on all the slices as well, and also on the black blood images. So the two landmarks, well, here we got the first bullseye, and the second one is here. And the first one, well, the landmarks to locate the region here and here. So this bullseye is a 16 segment mode bullseye to show the scar volume expressed as a percentage of the wall in each segment. For example, the 100 means they are full of scar in this segment, and 0 means there's no scar in this wall segment. Yeah. Well, to see the scar volume. I mean the how many pixel in this segment. Well. Because I already get the scar here. I mean, based on this result, I got the scar part. So I just got the number of the pixel of scar, and then calculate the percentage of the scar in the wall. Well, the scar. No.
You said, I think, like with the combination of bright blood and black blood, if I'm not mistaken, you train your AI model to detect the scar, right?
No, as I said, we didn't use artificial intelligence to detect the scar. We use a filter to get the scar. Well. Yes, based on the intensity. Yeah, based on the intensity, but it's a fixed one. It will not move as when I adjust the intensity. Yes, that's a work of the filter. So the filter does his work to get the good quality. Yeah. So for the second bullseye, one of the landmark get the start point of the calculation here, and this bullseye shows the scar transmurality for each slice. So here we can see the ring in the bullseye is corresponded to one slice. Each ring corresponded to one slice, and each slice is divided into 100 equally spaced chords, and then each segment represents the scar transmurality across one of those 100 divisions. And at the same time, we can see here some data results are provided as well. So for this patient, he has around 40% scar in the myocardial parts. Well, I need to back to the presentation. Yeah. So here I give you some information that I mentioned or not during the demonstration. Maybe it's a little bit clearly. So kind of summary, we have three functionalities: auto segmentation, scar detection, and scar quantification. And for auto segmentation, we can choose a region, the AI model to use. And in order to load the AI model, we use the ONNX runtime library, which works very well in C++ program. And for scar detection, as I said before, we apply Otsu filter to detect the scar. And Otsu filter select a threshold that maximum the variance of the threshold black and white pixel, so as to best extract the target from the background. So in our case is to detect the scar. And we set the threshold to 3 in our case. And after that, we use 2 bullseyes for scar quantification. The first one is 16 segments mode bullseye, which is used to evaluate the percentage of scar in the wall for each segment. And the second bullseye is used to evaluate the scar transmurality at 100 equally spaced chords in each slice. And so here is some screenshot of our main functionalities that, as I showed in the demonstration, for the auto segmentation and for the scar detection and for the 2 bullseye for scar quantification. So to summarize the presentation, due to the complex, slow nature of current MRI systems, we aim to propose a fast, one-click, fully automated and comprehensive imaging pipeline, of course, applicable for cardiology diagnostic. And we are building a platform for this purpose based on automated spot framework and applying in MusicCardio software. We implement a toolbox in MusicCardio software for automated segmentation, myocardial scar detection, and scar quantification. And our platform is still in development stage. So maybe in the future, we will add some new functions based on other program of our colleagues, for example, T1 row mapping, FET detection, etc. And there's still some bugs need to fix always to ensure stability and reliability. And further testing with more patients and requests as well to improve the algorithm, especially to enhance the accuracy of scar detection. And we also need to optimize our algorithm to improve the performance, such as enhance the processing speed and efficiency to give the result to doctor faster. And our ultimate goal is to create a pipeline or even another software in the future to give all the information to doctor with just a one click. So thanks for your attention. And if you still have got some questions.
Thank you for your presentation. Anyone have a question? Yeah.
Yeah, so how did you get to use OTSU instead of like standard deviation like in LG?
The filter.
The filter, the
Why I
filter
chose this
for
one?
scar
Because-
segmentation.
Well, I try a lot and this one works well.
How do you find work well? You test it with something or it just like visually it work the best?
Well, I test, I forgot the name, but several filter which can get the target from background in fact, to get the black and white pixel, to separate the black and white pixel. And this one, when I try several threshold, so the OTSU is the best one visually, yeah.
Is there a plan to like verify it if it like correct
Yes,
compared
there
to
is
the
a
real
correction.
scar or
Well, there is
manual segmentation?
yes, before I well, yes, of course, before I use a filter, this filter, I need pre-processing.
Yeah.
That means I need to adjust a little bit the intensity, just in case in some blackboard image is too black. That means visually we cannot see anything. So in this case, we need to adjust a little bit the intensity to make it already we can already see the difference between black and white pixel.
Yeah.
A little bit. Well, it's a parameter tests.
Yeah, I'm asking because in LG, because I used to work with LG image and nobody agree on how you define the threshold for scar. So they use standard deviation, full width half maximum, a lot of gray zone that say it is a part of scar or not. And my question is there a plan to like verify it if OTSU is gonna be like the best one to quantify the scar?
Well, I
It's
have
like the-
I have no proof theoretically proof to say that the OTSU is the best filter for that. But until now it works
Yeah,
well,
it works.
so we keep it.
Good, thank you.
Any more question? No, I got one. Can you apply this segmentation in 3D images?
For now, no. Well, in music cardio software, yes,
Yeah.
but in our toolbox, no, not yet.
Okay, and what about the resolution? You can work with any resolution with your image?
DICOM, Resolve,
No, with when you make some image, you know,
yeah.
you can put this segmentation with every resolution.
Yes,
There's no threshold. You know what I mean?
no,
No?
no.
Never mind. Okay. Any question?
Thank you very much. So after this algorithm generates everything, you get the segmented scar. Clinicians then have to believe that it's correct. Is there any validation that you've done with this in animal studies? Kind of going back to what Laura said too, if you could apply this to some of the studies here, you can do histology, some CT things afterwards to prove that the
No.
filters you're using, all these things are doing are giving you the exact answer.
For now,
Have you
no.
guys done this yet or plan to do it?
Well, maybe in the future, yes. But now in fact, I just began this project for 6 months, and the result is just to show. We use an algorithm that Aurélien proposed to apply it now, and the test maybe in the future we will do some test to verify if it's correct. detection or not. I think, of course, we need to do that, but for now, we didn't do. We do nothing for now.
That's William has been using some of my partnership to find our approach to what extent they use it to validate the model. I know they have some experiment data.
Yes, for the algorithm that Aurélien proposed, he already did a lot of experiments, but for the application, we haven't yet, use it by the doctors, yeah. It's still in development stage.
Any more questions? No? Because I thank you, Kun, and I think we are done for tonight. Thank you, everyone.